So let's say if we have a vessel filled with water, and on the inside we have a sphere. The fluid is going to exert a force on all directions on the surface of the sphere. So all of these inward forces exert a pressure on this object. So whenever you place an object in a fluid like water, the volume of the object will decrease due to the internal forces that compress the object. So the original volume may be like this, but the new volume will be slightly less. So this is the original volume, this is the new volume, or the final volume. So the change in volume is always negative. It's V final minus V initial. Now, if you saw my other videos on elasticity, Hooke's law, Young's modulus, and things like that, perhaps you've seen this equation. Delta L is equal to 1 over E multiplied by F over A times L0. And this equation applies, let's say if you have a rod and you apply a force to stretch the rod. So L0 is the original length of the rod. And once you apply the force, the length is going to change. It's going to get longer if you apply a tensile stress to it. A compressive stress occurs when you compress it. So this is the new length. So delta L is the change in the length. It's the difference between this point and this point here. Now this equation is very similar when you're dealing with when you put an object like a sphere in water or in any fluid, the volume is going to change. And that volume is based on the bulk modulus, which is based on the property of the object. And it's going to be negative because the volume will decrease. It's not going to increase. And we're still going to have F over A, just like we have here, and then times the initial volume, or the original volume. So notice the similarities between these two equations. Now, when dealing with fluids, instead of speaking of force and area, it's best to think of pressure. Pressure is force divided by area. And it turns out that stress is also force over area. So for fluids, pressure is the equivalent of stress, which is applied to solid objects. Let's say if you want to stretch a rod. Force over area is stress, but it's also pressure. So what we can do is replace F over A with P, since force over area is pressure. So the change in volume is negative times the pressure times the original volume divided by the bulk modulus. So this equation is helpful to calculate the change in volume when you place an object in the fluid. Now the bulk modulus is the ratio between the bulk stress and the bulk strain. And as you've seen in other videos, the bulk stress, or stress in general, is force over area. And the strain is the change in volume divided by the original volume. Now this is going to be negative. Delta V has to be negative because it decreases. So we can replace this with P. So the bulk modulus is equal to the pressure divided by the fractional change in volume. Now let's work on this problem. An aluminum ball with a radius of 0.5 meters falls to the bottom of the sea where the pressure is 150 atm. That is atmospheric pressure. And we're given the bulk modulus of aluminum. And so we need to find the original volume of the ball. So let's say this is the ball before we drop it into the sea. Once we put it into the sea, it's going to get smaller. Due to the very high pressures at the bottom of the sea, the fluid is going to exert a force on a ball from all directions, causing it to shrink in size. So let's start by calculating the original volume of the ball. So we're going to assume that it's the shape of a sphere with radius r, and the volume of a sphere is 4/3 pi r cubed. So we have the radius of the sphere. It's 0.5 meters. So this is going to be 4 pi times 0.5 raised to the third power divided by 3. So the original volume of the sphere before we put it into the sea, it's 0.5236 cubic meters. Now part B. What is the change in volume? So the equation that we need is this equation. Delta V is equal to negative P V initial divided by B. However, we need the pressure to be in pascals, which is newtons per square meter. Right now the pressure is in ATM, so we have to change that. So let's convert it. Let's start with 150 ATM. And you need to know that 1 atmospheric pressure is about 101,325 pascals. So it's 150 times 101,325. And so we can round it and say it's about 1.52 times 10 to the 7 pascals, or newtons per square meter. So that's the pressure, which I'm just going to rewrite it down here. So now let's calculate the change in volume. So this is going to be negative P, which is negative 1.52 times 10 to the 7 times the original volume, which is 0.5236, divided by the bulk modulus, which is 70 times 10 to the 9. So the change in volume is very small. It's 1.137 times 10 to the negative 4 cubic meters. So the new volume is not going to be very much different from the old volume. We know that delta V is equal to V final minus V initial. So if we move this to the other side, we can get the final volume. So the change in volume plus the initial volume is equal to the final volume, which is going to be 0.5236, that's the initial volume, plus the change, which is 0.000137. Now keep in mind, the change in volume is really supposed to be negative. So let's not forget that negative sign. So this is really, let's get rid of this plus sign, and that's supposed to be a minus sign. So it's 0.5236 minus 0.000137. So the new volume is a little bit less. It's 0.5235 cubic meters if you round it. So by dropping the aluminum ball to the bottom of the sea, the volume decreases only slightly. The bulk modulus of aluminum is pretty high, and the bulk modulus is inversely related to the compressibility of an object. So because it's so high, aluminum is not very compressible. So I want to compare it to something else. So keep in mind the bulk modulus of aluminum. It's 70 times 10 to the 9. The bulk modulus of a liquid like water is 2 times 10 to the 9. So because aluminum has a higher bulk modulus than water, it's a lot harder to compress aluminum, but it's a lot easier to compress water. Now air has a bulk modulus that is much less. It's like 1 times 10 to the 5. Now the units is newtons per square meter. So air is a lot more compressible than liquid water because it has a much less, a lower bulk modulus. So as the bulk modulus decreases, the compressibility increases. So these two are inversely related. It's interesting to note that the bulk modulus is basically the same as the atmospheric pressure at sea level. But now let's move on to part D. What is the bulk stress on a ball? So what should we do in order to calculate the bulk stress on a ball? The bulk stress is force divided by area. And we know force divided by area is the pressure. And we have the pressure in pascals. So the bulk stress is 1.52 times 10 to the 7 pascals, or newtons per square meter. So that's the answer for part D. Now for part E, the bulk strain, that's going to be the fractional change in the volume of the object. So it's the change in volume divided by the original volume. Now the change in volume is 1.137 times 10 to the minus 4. And the original volume is 0.5236. Now let's not worry about the negative sign. So the bulk strain is going to be very small. It's 2.17 times 10 to the negative 4. And it's unitless. The change in volume is in cubic meters. And the original volume is in cubic meters. These two will cancel. And so the bulk strain doesn't have a unit. And so that's it for this video. So anytime you submerge an object in a fluid, the volume is going to decrease. And some objects are more compressible than others. Basically, gases are highly compressible. If you notice, air had the lowest bulk modulus. It was 1 times 10 to the 5. And solids are very difficult to compress. They're almost incompressible. But gases are highly compressible. Liquids are somewhere in the middle, but not as compressible as gases.